All right, good day, everybody. Welcome. Good to see everyone. Hope you all had a nice weekend and are doing well. Very excited. I did some chair maintenance. You will not hear any more squeaking on my chair. I don't know if it bothers you. It drives me crazy when I listen to it. I also say an excessive amount. I realize when I watch, that's going to be a lot harder to fix. That's psychological, but the chair is fixed. So no more squeaking for now. And okay, so today we are going to pick up with the material that we started just before the exam, which was dealing with systems of differential equations. So just to kind of see the bigger picture for the semester, so far we've done first and second order differential equations. The second order differential equations had constant coefficients. That's what you guys were tested on Wednesday. The next exam, which is like mid-November, I think, some point, is going to be just on systems of differential equations. So we're going to be working in chapter 3 and chapter 8, dealing with systems of first order differential equations. And then after that exam, we're going to take a look at second order differential equations again, where now we might not necessarily have constant coefficients. That material we'll talk about after exam 2, and your third exam is going to only be on that material, just so it's clear. So that last exam is on much less material. It'll be shorter, and that's why that last exam is not worth as much points as the first 2. So we don't have like a comprehensive final in the class. But certainly you don't want to forget what we've done with first and second order differential equations. So any questions about that plan? So for this week, kind of the workflow is you had no reading quiz today. You do have one for Wednesday, and you have a homework assignment up, which is going to be due next Monday as well, on systems of differential equations. So I just want to mention a couple of things to you guys, just talking to the grader. So a couple of comments that she passed along that she would greatly appreciate your help on these. So your homeworks have been good. Just, please try and keep things neat and organized as best you can. I realize we're dealing with some technology issues that might be beyond your control, but just please try and do the best you can with that. And so the grader specifically asked if you can box your final answer and don't box other things. She said highlighting or boxing is fine. But that definitely helps her hone in on your final answer. So that might be one way to keep things nice and organized. And the other comment was that I don't think it's happening a whole lot, and I'm sure it's an honest mistake, but please just make sure your stuff is uploaded in the right order. So you should be able to preview it after you upload. And if there's a problem with the upload, you can upload again. And once you run out of 2 submissions, then that would be it. So please just make sure everything looks in order. She didn't say this to me, and actually I don't know if this is an issue, but when you're handing in your work, you just need to hand in your final work. So if you've done some scratch work to get you to the final answer, what you hand in should be a nice clean version. Yeah, we've been talking about showing your work, and kind of one thing that the grader also said was there are a number of people that are doing work in columns, and that's fine. But if you're going to do things in columns, just please try and like box around your problem so it's clear this work is for this problem, this work is for another problem. And just as an idea to see what some of your classmates are doing, I just want to share one of them with you. Where did I put that? Any questions while I'm finding this? And let me share this with you. So here's an assignment. Hopefully you guys can see this. This was the last one. And this is what she indicated as like, this is really nice work, which is easy to follow. So you can see the boxed in stuff. The work follows pretty clearly, very nicely organized. So this would be great for something like this. And I just want to point out here, you can see why the two columns might be a little bit confusing, because if I'm reading this work, I might think that like I read across or something like that. And so it can be confusing. If you're reading this, you might want to read it like that. So just put bars or boxes around things, and that will make it easier. I did that really messy, but that will make it easier for her to see which work deals with what problems. Any questions? Okay, so please, I'll include these notes. I'll add it to the homework in case you just forget it. I'll add some of these bullets so you keep it in mind. Okay, so last time we were working with systems, so I want to jump back into that. Unless there's a question, feel free to chat them in or ask them in. Okay, so this last page is actually the last page of what we were working on last time. So just to kind of recall, we were working with this differential equation over here, which was this rabbit and fox problem, which is a predator-prey model. And we were trying to look at the dynamics of this, and then we kind of were talking about there's different plots that we can consider. We can consider how the rabbit population changes with time, R versus T, how the fox population changes with time. Usually what we're most interested in is how the rabbits and foxes are related to each other, and we can include time in that picture in another way. So that's what I want to talk about here. So typically when we're graphing systems of differential equations, we'll graph the two dependent variables on the same axis. And when we do this, we call this the phase plane. And so this is kind of the equivalent of a slope field that we looked at earlier. And so in the phase plane, the way that we're going to approximate solutions is using what's called a vector field. And it's just a higher dimension, well, not even, it's just a type of slope field. And this is going to help tell us quite a bit about the dynamics. So we can go ahead and think about how we can calculate these different slopes. So we could take at time 0, let's say we start over here at 2, 3. So we're going to start at 2, 3, and here's this point right here. And what I'd like to know is at time 0, what's going to happen to the population? Are the rabbits going to go up, the fox is going to go up or down? And so we can identify whether R goes up and F goes up by looking at the RDT and the FDT. So this is kind of like the Euler's method sort of approach. So I can plug 2 and 3 into this system, or in this case, into this differential equation and simplify. And that gives me something like minus 2.4. Okay, and again, this we would get by taking 2 and 3 and plugging them into this differential equation over here. And then I can plug 2 and 3 into this other differential equation over here and figure out what is the FDT. And that gives us 1.8. So from this analysis, I can see that the rabbit population is going to go up, or excuse me, going to go down. And the fox population is going to increase, right, because of the signs of those slopes. And then in the slope field, we're plotting the relationship between r and f. So the vector that we're going to plot is df dr. And the way that we can plot this is by taking the f dt and dividing it by the r dt. So I take the ratio of 1.8 over minus 2.4, and that gives me minus 0.75. So this tells me the slope of the vector that I'm going to draw right here. And so I'm going to draw something which has a negative slope. And so I'm not going to be too concerned about that slope being 0.75, but we are going to have something negative. And so the issue is that's a negative slope. And so we could head in two directions. We could head in that direction, or it's possible that we head in that direction. And so that's where these individual slopes come in handy. So looking at this, I can see that r goes down, so we should be moving to the left, and f increases, so we should go up. Right, so we're decreasing in the horizontal direction r and increasing in the vertical direction f. So this means we would want to draw a vector which goes up and to the left, like that. So this would be the vector that I have in my vector field. And so now the path that I draw, we can see that I'm going to start moving in that direction, up and to the left. And then we can do a similar analysis over here to see what happens at time 2.07. And in this case, we can plug in these values, which is 0.756, 1.43, into these two different equations to get the r dt and the f dt. So I'll kind of share that calculation with you. And so now we can see, let me keep my color coding here. That this also is going to have a negative slope altogether, but here we can see that we're going to move to the right and down. And then taking the ratio of these, we can see that we get a slope which is negative again. But now we're going down and to the right, so it would look something like that. And then last time we looked at the entire vector field and we saw that we had some sort of cyclic behavior like this. And so when you're drawing things in the phase plane, you should be drawing what is the curve of our solution and what direction are we moving along that curve. So you also need to include a direction, which we can see over here is going this way. So we usually put arrows on our curve just to, and that's how we indicate time in the midst of this picture. Any questions? Okay, so then let's check some of these. So right, we can fill in vectors everywhere throughout the plane if we want to, like we can with slope field. So I can plug in these other values. And one thing that you might notice is if I plug r equals 1.25 into df dt, I actually get 0 always, no matter what r is. If I plug in 1.25 for r, excuse me, we're gonna get 0 no matter what. So you can check each of these is gonna wind up giving us 0 and 0 and 0 and 0. And then we can plug these values into the r dt, and we get these. And so when we take dfdr, we would get 0 over these non-zero things. So the slopes are all 0 at those points. And so if dfdr is equal to 0, this means slope is 0. Which means we're going to have horizontal vectors that are either going to point to the left or right. So I can come into this vector field. Here's this line when r approximately is 1.25, and then I know all of the vectors on that line are going to point horizontally. Any point in the phase plane that has r equal 1.25 going to have a horizontal vector. And to determine whether that vector points left or to the right, we look at this column over here. And so we can see that the ones that are positive are going to point to the right, to the right, to the right. And at this one, because the RDT is negative, we're going to get a point to the left at that moment. And if I drew this somewhat accurately, then what you should see is those that curve should be kind of tangent at those 2 points. So that's kind of where the path changes from moving down to moving up, or vice versa. So we calculated a bunch of these, and now we can see that all of these vectors over here are going to point either directly to the left or directly to the right. And the way that you determine whether it's left or right, again, is by looking at the sign of the horizontal derivative. Good. Any questions?
How do we find 1.25 for R?
We'll talk about that in a second. Yeah. So for now, let's just say that's a nice observation. And then, yeah, the next thing is going to be, well, how do we identify values where that happens? We'll talk about that next. But here's kind of the full slope field, or excuse me, vector field for this example. And remember, we used a different plotting tool last time to kind of look at these dynamics and these different views. And now you can see that we're getting exactly this behavior of all of these vectors along this line are pointing directly horizontally here. And then at some point, it changes and points directly to the left. But that's pretty special. That's not happening along other lines, at least most other lines. So typically, right, we use technology to graph these things, but you should be prepared to not necessarily graph these things by hand, but to be able to know how to use them and how to read them. Okay, any questions about this example before we check out another one? Okay, so let's check out another one then. Yeah, so now let's take a look at one where we don't necessarily have a practical interpretation. We'll just think about X and Y, and we've got this system of differential equations. And so let's make a plot over here. We'll do one by hand and then talk about some interesting properties here. And so I'd like to divvy up the labor, if we can, as follows. So here's a Word doc. If there's anybody that is not on here, I'll check it out. But what I'd like you to do is take the point that I have assigned you and calculate what is, oops, dy dx. And let's see. There should be a way, I think you guys can annotate this. Is that true? Maybe you can either just type it right in on the document. If you're not able, there should be a little button up top that says annotate. If you're not able to do it, then you can just chat it over to me and I'll enter it in. And just to be clear, we're using a different differential equation now. This differential equation, which is here's the system down here. All right, looks like we can annotate here. Yeah, I guess you guys can draw or type. And as you're sending these in, I'll be drawing them. Thanks for those that are getting chatted in. Okay, I think I'm getting them as they're coming in. Okay, so great. Let's take a look at how we're going to try and plot these now. And I want to be careful. So let me take the first one that Abraham did. So Abraham got -1. That looks good. So the question is, if I'm going to draw this vector, it is negative. So this vector can go down like this, or it can go up like this, right? Both of these arrows have a negative slope. So Abraham, which way do you think it's going to go? Is it going to point generally up, or is it going to point down?
It's going to point down.
And
down.
How did you determine that?
Because dx dt is positive, so it's going to go to the right. And dy dt is negative, so it's going to go down.
That's right. Yes. Good. Thank you. So we don't want to lose the information that we got from doing the x dt and dy dt, right? Because that helps indicate which way we're going, up or down. And so, great. So we're seeing lots of undefined things over here. Thank you. Ah, I see. And so all of these are undefined. And for the folks that were finding that these were undefined, and I think this one should be undefined over here as well. Why were these undefined? For anyone that got one of these, do you mind just sharing your thought there?
dx dt was 0.
Okay, good. So that means we're dividing by 0, right? Because when we find dy dx, we're taking dy dt over dx dt. And so if dx dt is negative, or excuse me, is 0, which is the case for all of these, that means there's no horizontal component. So all of these vectors over here are going to point vertically. They're going to be either straight up or straight down, depending on the sign of dy dt. And another thing that you might have noticed or picked up on is that all of these points like this one, and this one, and any point that I asked you to do that had a 0 for x and something non-zero for y, these all have the same slope. I can't highlight this, but yes, this is the idea over here. So these, any point that has x equals 0, y not equal to 0, we get a negative value. And so one thing that I want to make sure that you guys are really clear about is, does it make sense how we're determining in each of these cases, like which vector are we picking, since there's a choice of 2 vectors that might have that slope? Okay. So let's check out the full picture then. This could be dangerous. I hit the wrong iPad to share. Apparently that's my neighbor's. Let me stop that. Sorry, this is taking a second. I'm glad we did not see what my neighbor was looking at. Okay. So here's the vector field for that example, which was dx dt y minus x, dy dt is minus y. So I drew a couple of lines in here. And so one thing that we might have noticed in our table has the x dt equal to 0, right? So that's why these vectors are gonna, if the x dt is 0, these are gonna be vertical vectors, either up or down. And here we can kind of see if I drew it perfectly through those points, these are all points where things are going straight up, and we can see on this side, they're coming straight down. This line in green so any point on this line, x equals 0, has slope -1. They're the same everywhere along that line. And that's all of these over here. They all should be parallel to each other, and at some point doesn't change slope, it just changes direction. And one last observation. So any point on the line y equals 0, that's going to have dy dt equal to 0. So those vectors are going to be horizontal. There's going to be no vertical component to them. And that we can see over here. It's hard to draw, but these are pointing directly to the left. And these are going directly to the right. And let me just say that we don't need to have technology or the full vector field in order to describe the dynamics, what's going on. So ultimately, we might like to say, what is happening to x and y as t goes off to infinity? And this vector field is going to help indicate that. Even if we just sketch a couple of vectors, that might be enough to indicate the direction of things, might be enough to identify equilibrium and see whether those equilibrium are stable or unstable, like we did with the slope fields. And there's one particular point of interest here, and I should kind of amend some of these to say not quite any point. There's one really special point where these things intersect, and that is where we have an equilibrium. So at 0, 0, we have both dx dt equals 0 and dy dt equals 0. And last time we talked about when both of those are equal to 0, we call that an equilibrium. Okay, any questions? Okay, so if not, then a couple of definitions relating to that previous example. So first thing to note is that when all of the vectors along a line have the same slope, we call that an isocline. And let me just say this stuff, nullclines, isoclines, are actually not in the textbook notes on diffie-qs. So I added supplemental materials from another textbook, my textbook actually, that talks about nullclines. So that might help give you some extra reading outside of class. So these are when we have all vectors that have the same slope along a line, any line, or any curve for that matter. And then there are a couple of special cases, which is these cases where dx dt was 0 or just dy dt was equal to 0. So all of these things are isoclines. when we have dx dt equal to 0 and dy dt not equal to 0, then we call this an x nullcline, meaning all of the vectors along that line have dx dt equal to 0. And that means on x nullclines, we're always going to get just vertical vectors, either up or down, depending on the sign of dy dt. And this case down here in red is where we would have a y nullcline. And these vectors are going to be horizontal. And then last time before the exam, we did talk about how we can find equilibrium by solving a system of equations. So that's what's kind of outlined over here. So we have kind of these x nullclines where the x dt is 0, and then we have these y nullclines where dy dt is 0. So the process is, I think, fairly straightforward on how to find these. To find x nullclines, we set dx dt and equal to 0 and solve. Whoops. And to find y nullclines, and we solve. And in these cases, you shouldn't expect to find like one unique solution, but rather an entire line of solutions, usually. And we might have more than one nullcline. Any questions? Okay. So it's an algebra problem. So if we wanted to find the x nullclines for this example, then we take, keep my colors here, we would take 3x minus 1.4 xy, and we set that equal to 0. And let me just say here, this is the rabbit fox differential system of differential equations. I just changed r to x and I changed f to y, but it's the same system. So you can think about x and y in practical terms here if you like. And so how could we solve that equation? You can chat them in if you don't want to chat to everybody. Any thoughts on how we could solve that equation? What's a good plan to do when you've got left side equal to 0? What usually helps factor out an x. Yes. Thank you. We can factor out a constant as well, but yes, we can definitely factor. Let me just say, you would want to factor here as opposed to say divide both sides of the equation by x, because you don't want to assume that x is not 0. So I'm going to factor this. We can factor an x out, and then what's left is 3 minus 1.4y is equal to 0. So we've got a couple of solutions here. X equals 0, that's going to be an x nullcline. And if I solve 3 minus 1.4y equals 0, then what do we get for y there? That comes out to approximately 2.14. Any questions about how we found those two? Okay, so I'm going to draw my null clines in. So here's x equals 0. And here is y is equal to 2.14. So kind of there's a two-step process, let me say. So step one is set this equal to 0 and figure out what the null clines are. And then there's a second step, which is determine whether they point up or down. Okay, and we're going to determine that based on the sign of dy dt. Okay, here we go. So let me just do a little bit of scratch work over here. So now we're going to kind of deal with this stuff over here. And so we had a differential equation dy dt was equal to minus y plus 0.8 times xy. And we had two null clines. And so we need to check the direction on each of those null clines. So for the first null cline, when x is equal to 0, we can plug this in to the differential equation and we get dy dt is equal to minus y. So we can see that the vectors are going to point up. Dy dt is going to be positive when what is true about y. What values of y are going to make the vectors point upwards?
Negative y values?
Yeah, that's right, because this is changing the sign. So this is going to point upwards when y is negative, and dy dt is going to point down when y is bigger than 0. So that means when y is bigger than 0, these vectors point down and down and down. And when y was negative, we said the vectors were pointing directly upwards. Okay, so we can see along that line, things seem to be heading in towards the origin there, directly into the origin. Any questions? This gets a little bit trickier than when we were just checking individual points, because now we're going to find that the sign is going to depend on conditions of X and Y. And we just need to adjust them accordingly. Okay, and so then taking a look at the other line, we would plug this into dy dt, and then we can simplify. So what do I get when I take 0.8 times 2.14 okay, sorry, just plugging in the 2.14 in for y and simplifying, and then you can see that this is going to be bigger than 0 when, I think I missed the sign here, right? The dy dt was minus y, 0.08 xy. And so plugging in this into the differential equation, we get this, and then we want to think about for what values of x is that going to be positive. So when x is bigger than 1.5, we have dy dt is positive, so these are going to point up. And when x is less than 1.25, dy dt is negative, and these vectors are going to point down. So here's about 1.25. And again, what we said is that when x is bigger than that, it's going to point upwards. And when x is less than it, it's going to point downwards. And notice it's consistent with the direction that we found on the other null cline. Okay, any questions? Okay, what I'd like you all to do is break us up into breakout rooms is to do the same analysis with the y null clines. So I want you to figure out, first of all, what are the equations for the y null clines? You should find 2 of them, and then determine the direction, which is going to be either to the left or to the right, looking at signs of dx dt. And that process would be similar to what we did down here. So you need to do this separately for each null cline. So I'll just say you should find two null clines, 2 y null clines, similarly to how we did x null clines. Any questions before I break this up? Okay, so the rooms are open. Please don't just zoom ahead on your, no pun intended, don't just pile ahead on your own. Make sure your group mates are with you. So it definitely helps to talk about this with classmates and communicate it. And if you have any questions, just hit the ask the instructor button and I'll check in on you. Hello, welcome back, everyone. So great, I only had a chance to check in with a couple of groups. So based on those discussions, oh, sorry, not everybody's here. I think everybody's here now. Hi, everyone. So just checking in with the groups, it seemed like it was just a couple that I checked in on, but finding the null clines went okay. And that comes from just setting dy dt equal to 0 and solving that equation. And there were two null clines for that. There was one at y equals 0, I believe. That's pretty clear where that one comes from. And then there is a second one at x is equal to 1.25. So any questions, at least, about how we can identify those from the groups that I didn't get to? So there's one, and here's the other. And then we want to determine the directions on those. And I think it's yeah, so when y is equal to 0, and we now would be checking the signs of this, I believe that these should be pointing to the right. And they're pointing to the left over here. So depending on whether x was positive or negative, the vectors are going to point to the left or to the right. Did anybody have any questions about that? And I did the work down here for figuring out the direction along the line 1.25. So you would plug in 1.25 into that differential equation. And then basically you can set it equal to 0 and then determine what values of y make it positive and what values of y make it negative. So we can see that when y is bigger than 2.14, it points to the left. So we get vectors that are pointing this way. And then when we drop below 2.14, they change to this way. Any questions? And so here's what's really nice about nullclines is that they divide the region up into areas where the slopes, the vectors in the vector field all have the same general direction. So if we kind of think about the rabbit-fox problem, let's just kind of think about what's happening in the first quadrant, since we don't really care as much about positive and negative values. And that is in this region over here, all of these vectors are pointing, sorry, this region in here, all of these vectors are pointing to the right and up. So all of these vectors are going to generally be moving in that direction in this region, all of them. Then we can look in this region over here, all of these vectors are going to be pointing up, but now we've moved into the region where they're pointing to the left. So now all of these vectors are going to point up and to the left, so they tend to go that way. And these nullclines divide regions where all of the vectors have the same general direction, since the only time a vector can change directions completely is if it passes through one of these nullclines, if it passes through a point where it's 0. So these point down and to the left, and these point down and to the right. So this gives us this cyclical behavior that we saw with the rabbits and foxes, and we did all of this without using any technology. So we can kind of see the general shape of the solutions there. And this point right here, that's our equilibrium, or at least one equilibrium. So when we draw all these null clines, how do you think we can identify where the equilibrium solutions are?
Where we have X nullclines and Y nullclines that intersect.
That's right. Thank you. That's right. So these equilibrium occur when dx dt and dy dt are simultaneously zero. So once we draw these null clines, we can also identify all of the equilibrium. We don't have to go back and solve another system of equations. And the thing that you want to be careful about here is that equilibrium at points where different null clines intersect. Okay, and so that's kind of the caveat there. They need to be different. So at this point over here, we have two y null clines intersecting with each other. That's not in equilibrium. Dx dt is not zero at this point. And the same over here. This place where the two blue lines intersect, this place where we have two x null clines intersecting, that's not in equilibrium because dy dt is not zero there, it's pointing down. So we have two equilibrium, one here and one here. And kind of here's the complete picture. And what we drew, we could already determine kind of the complete picture just by sketching in the null clines. And so this equilibrium over here that's going to be stable since solutions that start near that point stay near that point. And what's happening at the origin is a little bit more complicated. In some directions, we're going in, and some directions we're coming out. So we would call this point, this equilibrium at 0, 0, would either be called semi-stable or saddle. I'll just say it's called different things in different places. Some people will just flat out call this unstable, but to me, unstable is going to be no matter what direction we're in, everything flows away. So this is more commonly called a saddle point, since some go in and some go out. Okay, so I'll stop here since we're out of time. I will say that in the reading materials, let me stop this, on our Canvas site, yeah, so here's kind of the reading materials on null clines, and it'll look different format because it's from a different book, but there's a bunch of problems at the end for you to practice if you want additional practice on this besides what's on the homework. And I posted solutions to all of these problems as well, so you can check your work on them. But there's one null cline-esque problem on the homework, which is due next week. So you might want to get a little bit of practice before you give that one a shot. Okay, so thanks everyone. I'll stop here, and next time on Wednesday, we'll be working more with the phase plane and equilibrium and thinking about stability some more next time. And then we'll solve them. That'll come next week. Okay, well, thanks everybody. Have a nice afternoon. And if you have any questions about things, I've got office hours tomorrow. Otherwise, I'll see you on Wednesday.